So we're in the Geology Museum at UW-Madison, and we've got a number of exhibits that we can show the public about how we study the early Earth. These are photosynthetic cyanobacteria, the green. This is where we came from. And it's hard for us to relate to this as our ancestors, but this is how life existed on Earth for at least 2 billion years. This contains evidence for the first oxygenic photosynthesis on the planet at 3.2 billion years old. And there's just a few places in the world, one of them being South Africa, one of them being in Western Australia, where rocks of this age are actually preserved well and have not been metamorphosed. So that's where we have to go to find this record.
You see, we have this up-refining sequence.
Yep.
My name is Nick BEUKES, and I'm a professor in geology at the University of Johannesburg. To some degree,
Gets deeper. Right.
I specialize in very old rocks. Most of my time I've spent in rocks with an age between, say, 2 billion years and about 3 billion years old. But these rocks can all tell you something about the history of free oxygen in the history of the world. So as a central theme probably of my work, I always have this story about oxygen in the back of my mind.
This is basically
The reason why we worked together with the University of Wisconsin was initially with our combined interest in the origin of iron formations. Clark was very much interested in doing sophisticated analysis of iron formations, like, for example, iron isotopes. This stuff is so well preserved. And because I'm essentially a field geologist, I have a very good feel for the regional correlations and the regional picture of these iron formations. You know, I think it's anchorite. Yeah.
Nick is world famous in earlier studies.
Yeah, so I mean, that's magnetite.
We can supply the analytical tools,
Hematite will be more elongated, like specularite.
but Nick supplies the essential on-the-ground geologic experience with his decades of understanding of South African geology. And so it's really that mix of laboratory and field-based studies that is essential for making important breakthroughs.
This drill core we drilled last year, and the idea of this hole was to try and see if we can find biomarkers for oxygen-breathing organisms to be around. But so the core comes down that top, and then you go down like this, you start again there. If you follow it down, now we're at a depth of 230 meters, so we're now really pretty deep down. And as we come down here, I think it becomes better as we go deeper. And so out here, we now see the true, nice, fresh iron formation.
In the plasma.
And when Clark and his students worked on this, they discovered a very important thing, that these layers here have a different chemistry than these dark layers. So the chemistry of the layers that were washed in from shallow water they have a different composition to the ones that formed in the deep water.
And the reason that's important to figure out is that photosynthesis would only be restricted to the shallow oceans where light could penetrate. The deep oceans, light doesn't penetrate, and so if we're looking for a signal for early photosynthesis, it's going to be in those shallow water sediments. What's really rare is to find both shallow water and deep water sediments preserved in the same samples. And in this Barberton core, which is really unusual, we found both of those that have really revolutionized our ability to look at shallow water and deep water conditions and find that there was oxygen in the shallow waters at 3.2 billion years old.
But what is really the real origin? These are actually the origin of the organisms that started to breathe oxygen. So this is really the deep origins of humankind, if you want to call it like that. Also, you don't know that is very exciting. If I just have only this, I can make a story and say this is deep water, this is shallow water.
This rock that's so magnetite rich.
But it's only when you have guys like Clark around and then can do all these sophisticated analysis that you then see what more this rock can tell you. And that's why it's so important to collaborate. To understand the rocks a little bit better, you need people with different expertise to work on the same rock.
This is the Paleomag lab of the University of Johannesburg. So what we do here, basically we take a rock, and this core is what we run here. The information that we got from the core will help constrain what was the magnetic field that was recorded within certain minerals of these rocks.
Paleomagnetic signals in the red. So the development of the Earth's magnetic field early in Earth's history is really key to understanding the evolution of life on Earth.
The magnetic field, it works and kind of protection against rays that may come from the universe, and it blocks them. So if we were not to have the Earth magnetic field active, life will stop, because whatever is on Earth, living on Earth, will be destroyed by these rays. So I think the life started after the magnetic field was present.
We can start to see the sample actually.
You're not able to travel back in a time machine. We're not able to see exactly what it was. And the way we get confidence in our reconstructions of the ancient Earth is by getting multiple lines of evidence on the same type of sample. And we start to weave this story together about what the ancient Earth looked like by looking at this holistically with multiple ways at looking at the exact same samples.
They are very steep stromatolites.
If we go to a little bit younger rock, and by a little bit younger I mean going from 3.2 billion to about 2.9 billion, what we see is that the microbial world just exploded in diversity.
Almost like a little ripple.
Yeah, you can see it's also graded. I mean, you can see it's
These are rocks that Berta Smith has been studying at the University of Johannesburg.
basically microorganisms were living around this granule.
And what he's done is look at these microbial mats that have been reconstructed in this 3D imaging. And when he starts putting that in the context of our earlier work for oxygen photosynthesis, we start to then be able to put the evolution of the biosphere in kind of this temporal context, going from 3.2, 3.5 billion years to less than 3 billion years ago. And we see that the Earth was really evolving quickly and diversifying into these microbial niches in a really rapid pace.
It probably also shows that early life, a lot of it probably respirated, breathed iron, as it were. It used the oxidation and reduction of iron in its metabolism. Because today, for example, photosynthesis, you've got CO2 being converted to oxygen. When we breathe, we convert oxygen to carbon dioxide. Whereas these organisms, they essentially used organic carbon and iron, and they breathed iron.
And so one of the things that we need to do is to do experiments underneath early Earth conditions where there's no oxygen. There's no oxygen in the atmosphere inside this chamber, and that allows us to do manipulations with iron chemistry under early Earth conditions.
And we have liftoff.
We've done work with NASA for a couple of decades now, actually, as part of their astrobiology programs. And the questions of astrobiology are, what is the origin and evolution of life on Earth, and how likely is it that we would find that on other planetary bodies, find it elsewhere in the universe?
Touchdown confirmed. Receiving.
And NASA is interested in this because when we go to other planets such as Mars, our interpretive context comes from the only planet in which we know life evolved. And so if we understand what life looked like on Earth 3 or 3.5 billion years ago, we put that context in the back of our mind when we start looking at samples from Mars, for example. Do we find the same things, or was it different? And so studies of geology exactly feed into NASA missions in terms of searching for life elsewhere.
So it brings us back to our real origins. And when that oxygenic photosynthesis, which is the form of the modern life cycle, depends on that, and when did that really start to develop in the history of the world. And I think that's a good thing to study.